How are you, Professor?
Good, thank you.
That's good.
So let us start our lecture today. As I mentioned last week that I will give a review of Australian rainfall and runoff, chapter 3, book 2 and 3. And I asked the students to read these two chapters and prepared some questions for me. So is there any students who has read it and made any question for me? Whether you need any clarification or understanding for any of the issues in Australian rainfall and runoff, book 3, chapter 2 and chapter 3. Anybody read this chapter?
Yes, I went through like before the quiz. I went through like before quiz 1.
So do you have any question?
No, all good so far. Thank you. But I do have a question regarding the report, if you don't mind. Point 4, when comparing, or shall I ask you this in the break time?
Probably we can discuss the project report on a stage.
Yes, thank you.
So at this moment, I am asking that, do you need any clarification on any issue in Australian rainfall and runoff, chapter 3 or chapter 2 of book 3? Let us open this chapter, the ARR. Okay, so let me share the screen. So this is the Australian rainfall and runoff guide. So in this area of hydrology, if you are practicing in Australia, then you have to use this guideline, Australian rainfall and runoff. It has the guideline and the software and the data as well. So we can get the web-based version or PDF version. So let us look at the web-based version here. So I asked to read you book 3, peak flow estimation, and then first is the at-site flood frequency analysis. So what do you mean by at-site flood frequency analysis? Who can tell me? What is at-site flood frequency analysis? Can anybody explain? Or I have to ask maybe students probably.
Is it, Prof, for any specific site, in a specific location?
Yeah, that's right. At a specific site, at a specific location, we want to do flood frequency analysis.
Yes.
Using the recorded data at the site.
Yes.
So if there is no recorded flood data or stream flow data at a particular site, we cannot do at-site flood frequency analysis.
There is another method. There is another, I forgot the name.
So in at-site flood frequency analysis, what are the main steps there? If you want to do at-site flood frequency analysis at a particular site, say Nepean River, in M4 bridge, you have some data recorded there, and you want to do at-site flood frequency analysis, what are the steps you will follow? Any student?
So first, choose a distribution, like a method, like choose which one to use, like what kind of distribution. For example, log normal, GEV.
So that is one of the steps. So first step would be to obtain the data, to obtain the annual maximum flood data at the site and check the data consistency, check the error in the data. If there is any gaps in the data, fill that gap, and check the data for the consistency. So that will be the first step. Then the second step, you need to, if you want to use Australian rainfall runoff, then you will be selecting 5 or 6 distributions. What are these distributions recommended? Not recommended, but provided examples in ARR chapter 2. What are these distributions?
So this normal, log normal distribution and log Pearson type 3 and GEV distribution and I think EV1.
No, that's not right. Can you read your chapter and then find the answer? Because I can find it for you, but students, can you open your ARR in your website and find what are the distributions they have provided examples in ARR chapter 2. It's written in this book. What Tanzim is telling, that's not correct entirely. That tells me that none of the students have gone through it. So there are so many issues here and you are thinking that it's easy to understand. And if somebody says that I understand everything, I doubt it. So you see a choice of distribution family for annual maximum series. Can you see my screen? Tanzim, can you see my screen?
Yes, I can see.
Okay, so you see choice of distribution family for annual maximum series. So 2 distribution families are suggested a reasonable initial choice for AM series, namely the generalized extreme value and log Pearson type 3 families. Okay. And then they are giving description of the generalized extreme value distribution. So here they are listing the generalized extreme value distribution, Gumbel distribution. So what is the name of Gumbel? There is another name for Gumbel. What is that? Gumbel distribution is another name. What is that?
Type 1?
EV1, extreme value on distribution, EV1.
Oh, yeah, EV1. Thanks.
EV1. Students, most of the students, you are not really reading or listening. Most of the students. So log Pearson type 3, another distribution. Log normal, there is another distribution. They have kind of advocated for it. Generalized Pareto, another distribution. Exponential, they have not suggested it. So they have given 1, 2, 3, 4, 5 distributions. And the software that is called Flyke. The Flyke software is the software that is recommended for flood frequency analysis in Australia. That software has 5 distributions. There is no exponential distribution there for flood frequency analysis. So they have discussed each of the distributions here. And the Flyke software has inbuilt program there. So if you copy the data and put in the data input sheet, and then they will do the estimation for you for all the distributions. But this Flyke software is not free, but it is not very expensive as well. So somebody can buy it. If you need for research, they give you free for the university student. If you are doing some project or thesis on it, then they will give you free for that. Okay, so I think that is the second thing, that what are the distributions that you will be using? Initial SOS, GEV, EV1, LP3, log normal, and generalized Pareto. These are the distribution that you will do it, and then you will try to see whether your assumed distribution fits the data well or not. So let us see what are the other things in the chapter. So there are two things, annual maximum and peak over threshold methods. So what is the difference between annual maximum model and peak over threshold model? How do we construct annual maximum series?
So AM series is just the peak flow of each year, like the data for peak flow for each year.
That's right. And what is
And
about
for-
peak over threshold?
The peak over threshold is the one like where you decide that a certain threshold is selected for the flood, and then every year, even if there's like two data that has flow over that threshold, you choose both data for that key. But if you don't have a so basically you decide like what threshold to use. But yep.
So what is the guideline for selecting this threshold? How we generally select the threshold? Because if the threshold is too low, then you will get too many data points. Some of them they may not be the flood.
Isn't it
General
using the
guideline
good
is that
fit? Oh,
if you have,
no.
yes, go on.
I thought I was gonna say, isn't it using like the good fit analysis thing that you were doing before?
The goodness of fit test, that is
Yeah,
different
that one.
thing. That is to test which distribution fits your data.
Hmm.
But I am asking that if you are selecting peaks over threshold selection, then first you have to prepare your
that's
data
what-
set.
Yeah.
So in preparing that data set, you have to select your port series. In annual maximum series is easy because you are selecting the maximum value from each year from the hydrograph. But with peak over threshold method, what you do, a general criteria is that you generally select three values on average per year. So it means that if I have 30 years of data, then I will select the 90 values, 30 times 3, 90 values, which are independent to each other. So that's a criteria. Somebody selects 2 events per year. Even you can select 1 event per year as well, but then it will be 30 events, but irrespective of the year. The biggest 30 events, which are independent from each other. Then the question will be coming, how you do the independence check? When you're selecting your events, pick, how do you know whether they are independent or not? How you do that? The students, you are not reading or thinking or following anything. That's why if you get very low marks in the exam, that is an indication because you are not really following things. You're not giving effort to this subject. And that will be reflected in the exam marking. So the independence criteria of selection is that if you are selecting one event, then you should not select the next event until you have certain gaps between the events. So a general criteria is that you can select around 3 days. That depends on the size of the catchment. If the catchment is very large, then 3 days even not enough, you may have to select 7 days. Once there is a flood event, you have to wait 7 days until another event is independent. If the catchment is very big, it takes quite a bit of time to drain the flood water from the river. If the catchment is very big, like say Murray-Darling Basin, a very big catchment, 7 days is not even enough. You may have to consider 3 weeks even for that catchment. So it's a function of catchment area. The minimum time between the 2 events, that depends on the catchment size. So you have to do an analysis for that. And once you look at the hydrograph, you can easily find that whether one hydrograph has finished, and then you give some space, and then you select another hydrograph. So that is the way you do the independence criteria. There are many other advanced criteria, but these are some of the practical criteria that you select. You see here, they're giving an example that say these are 3 events here, and it's telling that independent peaks over threshold. So this, both of them, they are independent because they are satisfying the criteria, because you see this hydrograph has finished, and then there has been another small hydrograph, and then you see it went to the best flow condition almost, and then another hydrograph. It means that there has been a rainfall event, there's a big event here, then another small event here, and another big event here. So really this and that, they are independent, but this and this, they are not independent, because you see here, anyway, this is below the threshold anyway, so we don't worry with that. Selection and preparation of data, that I mentioned to you, that you need to select and prepare your data and check the data. For example, some of the things are here. Examples of change in collection of data or in the nature of the catchment that lead to lack of homogeneity are inability to allow for change of a station rating curve. So rating curve is a big problem. So if rating curve is a problem and it has a lot of error, that will affect your estimated values, and you should be very careful about it. Change of the gauging station site. Why we have to change the gauging station site in some cases? Why we have to change the gauging station site? Any idea?
So data may be unreliable in that gauging station.
Generally, it happens that sometimes due to very big flooding, there may be a lot of erosion, and your instrumentation site might be in trouble. So you may have to change your gauging location to a stable location as well. So it mainly happens after big flooding. If the control section, if the cross section that you used before, that has changed due to erosion, or it can happen due to deposition as well. If due to low flow, there has been a lot of sedimentation along your cross section, because you are measuring discharge, Q equals area time velocity, is that right? So area is the area of the cross section. If the area of cross section changes due to erosion or deposition, then your rating curve is no longer valid. So in that case, you may have to change your gauging site location. And once you change the site, by location, I mean that nearby, say M4 bridge in Nepean River, then you may go 200 or 500 meters up or down to find a good suitable location, or maybe a few kilometers up and down, depending on the condition. So then the problem will be coming that the data you collected before, they are not homogeneous as with the data that will be collecting later on, because your gauging site has been changed, that you are dealing with a new rating curve. So you have to consider that kind of thing. Construction of large storage, dam or levees, or channel improvement, if that has been done, then your data may not be homogeneous. Growth in the number of farm dams on the catchment. Farm dams are small dams built by the people in the farm. If there are too many farm dams in the catchment, that will reduce the stream flow, because these dams, they will try to retain some of the runoff. Change in the land use, as clearing, different farming practices, soil conservation works, reforestation, urbanization, this affect the catchment hydrology. So if these sort of things have happened quite a lot, then the data will be non-homogeneous, and you have to be very, very careful in using this data and interpreting the results. So this is the rating curve issue here. rating curve extension by fitting to an indirect discharge estimate. So this is the log of stage, means water level, and this is the log of discharge. This is the interpolation zone. The interpolation zone means that we have the data, both the stage and discharge within this part. So our rating curve is quite accurate in this region. But then the problem is we don't have enough measurement of discharge for large stage. So that means this is the extension zone. So we have to extend this point. It may be up to this way or that way, we really don't know. So there will be an error here. That is called the rating curve error, which is a significant error. Sometimes it can introduce 30 to 40% error in your reported flood data. Sometimes there might be some historical and paleo flood information. By historical here, we mean that it is not recorded in the station database, but there is some evidence that there is a big flood in some, say, 50 years back, but we don't have any discharge data accurately. But we have some indication of that. There might be some way by looking at the tree growth or sedimentation analysis, we might be able to find out what was the magnitude of that flood. That is called the historical or paleo flood information. So in FLIKE, you can consider that information in your flood frequency analysis as well. When you prepare your data, it may have your missing records. So if you have a missing record, for example, 2 year, say 1992 or 95, there is no recorded data. Maybe an instrument has failed. So during that time, you have to fill that recorded data. You can do that by doing a regression analysis between your station's data and the nearby station's data, or with the rainfall. You can do a regression analysis, and you can use that regression to fill in the missing record. And then that's coming is the choice of the flood probability model. So according to ARR, you should start with these 5 distributions, and then you see which one is fitting your data better. And of course, you can do goodness of fit test, like Anderson-Darling test, or Kolmogorov-Smirnov test, or chi-square test, to see which distribution is fitting the data. One of the software is free, that is called Easy Fit. If you can write it down, there is a software called Easy Fit. EASY, Easy Fit. It is a free software. Of course, you can buy it because there is an advanced version which is better. It has around 15 or 20 distributions, and you can check the goodness of fit test using 3 criteria. And really, it is very useful and very easy to use. Easy Fit software. You can write it down because in your professional career, it can be very useful. Easy Fit software. So in the Australian rainfall runoff, they have used the Bayesian criteria. Bayesian criteria is really, they assume that location, scale, and shape parameter, they are not constant, rather they are random variable. So they have probability distributions. It is a little bit more complex, but the FLIKE has inbuilt this method within the software, so people can apply it without doing complex mathematics. They have given some work example here. L moments approach. L moments are introduced by Hosking in 1990. So it has a history of around 30 years. So L moments are similar to like our mean standard deviation skew, but they are more accurate, particularly for short data length, and also if there are outliers in the data. So this is called L moments approach. I applied this technique quite a lot in my PhD research, this L moments approach. There are free software available in our program. which you can apply to calculate L moments. Okay, so is there any question? Any further question on this chapter? So you have a exam quiz next week, is that right? When is your
Yep.
next quiz?
It's next week.
Next week. So you will be expecting some question from these 2 chapters of this ARR.
Yep. I did want to ask you, will the quiz be 30 minutes or will it be an hour next week?
Sorry, can you repeat?
Will the quiz be 30 minutes as it says in the learning guide, or will it be more this next time we have it? Next
I
week?
think we'll give more time,
Okay, that's good.
similar to last time.
Okay, that's good.
It will be similar to the repeat quiz.
Cool. That's perfect. Thank you.
So you'll get more time basically. Last time I gave, I think 1 hour and 30 minutes, is that right?
For the
How much
repeat
time we
quiz,
gave last time?
for the repeat quiz, I don't remember, to be honest. I'd have to look through your
The
announcements.
repeat quiz, how was the time? How much time you got? Who
I'll
got
check
repeat
the
quiz?
announcements now.
So 1.5 hours.
1.5 hours. So the next quiz, do you want 1.5 hours?
Yes, please. That'd be perfect.
Okay. So I'll give you 1.5 hours. But
Thank
there will
you.
be questions on these 2 chapters because these are very fundamental. So this is the flight software. So the flight software looks like this. And then really you import your data by this way by clicking on the guest flow. And then you can see here, you can select the Bayesian method. You can select the LH moments. LH moments is another technique that is applied in the GV distribution mainly with Hayes equals 0 or Hayes equals 1 and so on. When you say Hayes equals 1, 0, it becomes L moments. And you see there are distributions here, log normal, LP3, Gumbel, generalized Pareto, and generalized extreme value.
So
you can
should we
select
have
which
this
distribution you
software
want to do it.
downloaded? So
And if you said
Sorry.
okay, then it will you will enter the data like this. And if you feel some of the data points they are outlier, then you can exclude it by clicking here. And you can do some gap fill years as well. And then finally, you will get the answer like this. Like this is the kind of diagram that it will generate for you, where it will plot your AEP and your log of peak flow. And these are the smaller triangles. These are your observed data. And this is the fitted distribution in the middle. And this is the confidence limit of the estimation. So it will give your estimation like this. Say 1 in YAP, so which is really 10-year return period. So this is the expected quantile, and this will be your confidence limits of the quantiles. So you can see for 100-year return period, in this case, your expected flow is 19,572 meter cube per second, but your 5% confidence interval is 7 on 8, and 95% limit is 107. You can see it's a big difference. So that means that there is a lot of uncertainty and error in this estimation due to limited sample size and due to, of course, it's mainly due to sample size. Okay, so I think that's all for about this chapter from my side. So I will give another chance if you have any question on this chapter. Now this chapter 3, the regional flood methods. This chapter, by the way, we applied this flight software to around 800 catchments in Australia. Me and my research team, particularly in the leadership of Khaled Haddad and many other persons. And we really have applied the flight software more than anybody else in Australia, basically. So we really have a very good understanding of this flight software. And we work with Josh Kuzer, the developer of the software, to test it and apply it. Okay, so this is the regional flood methods. So when we want to apply the regional flood method, can you tell me? When do we like to apply regional flood methods instead of at-site flood frequency analysis?
So when there's no data at a station, for example, an ungauged station, catchment.
What data you mean when you say data?
Stream flow data, yeah.
When you don't have any recorded stream flow data at a particular location where you want to get your estimation, design flood estimation, then you have to apply regional flood methods. So what is the fundamental concept of regional flood method? What is the fundamental concept of this approach?
So it transfers data from one to another location. So assuming that the region is like homogeneous, like the characteristics are similar between the two catchments.
You're right. So the concept is that although I don't have data at my site, but I can use the data from some other sites which are available, considering that my site, my ungauged site is homogeneous to some other sites. So that is the fundamental concept. Then we have to judge the homogeneity, how we judge the homogeneity or hydrological similarity between your ungauged catchment and other catchments where there are data you want to use it. That is one of the fundamental problems in regional flood frequency analysis. So this approach is mainly used for small to medium sized rural catchments. So you see here, estimation of peak flows on small to medium sized rural catchments. What is the upper limit of the medium sized catchments in Australia?
So 1,000 square kilometers.
So 1,000 square kilometers is a general guide that this technique is applicable to up to around 1,000 square kilometer catchments. And these are used for design of culverts, small to medium sized bridge, causeways, soil conservation works, and for various planning and regulatory purposes. So you cannot use this for a very big catchment. For example, if you want to estimate design flood at Windsor in the Nepean River, for example, your catchment is around 8,000 square kilometer. So you should not be applying this RFFE model there, because RFFE model is only applicable up to 1,000 square kilometer square. Then you have to use other approach. There are many other advanced techniques. Expert people, they can apply it, but this approach is up to 1,000 square kilometer. So in developing this RFFE technique, we adopted a number of criteria. What are these criteria? One is that national consistency and approach. So it means that similar kind of distribution we'll be using for whole Australia probably, or similar way of doing it by some way. So national consistency and approach, because the ARR 1987, they recommended different type of RFFE approach for different states. Smooth interface at the boundaries between areas. What do you mean by that? Smooth interfacing at the boundaries between areas. Can anybody explain that to me?
So the boundaries don't overlap between the catchments. So when you're like taking the boundary of the catchment, so make sure that
it's not the boundary of the catchment, it's the smoothing interface at the boundaries between areas. So for example, in ARR 87, they recommended a technique for New South Wales. Another approach was recommended, say, for Queensland. Now, in the border of the two states, a part of the catchment may be coming from Queensland and part is coming from New South Wales. Then which technique we want to apply? Because there are two different approaches recommended for two different states. So that will create some issues. That is called the boundary problem. Use readily accessible data. So that is mean that the RFP model, if you want to apply it, it should use the data as a predictor variable, which are easy to obtain. For example, catchment area or rainfall intensity, they are easy to obtain. Utilize as much of Australia's stream flow database as possible. So the bigger number of stations you use to develop RFP technique, more accurate your RFP method will be. But of course, when you are using the data, then data has to be accurate. It has to be certain length of the data, certain quality has to be satisfied. We have given a definition of regional flat frequency analysis here. So it has been defined that RFFE is a data-driven approach, which attempts to transfer flood characteristics from a group of guessed catchments to unguessed locations of interest, where design flood need to be estimated. So what are the different steps in regional flood frequency analysis?
So as per my understanding, for regional flood frequency analysis is the mainly two steps. First one is to identify the homogeneous regions, applying various available methods, and then develop the regression equations for the quantile estimation. These are the two main steps in regional flood frequency analysis.
I think you're right. So first step is the formation of region, means that what are the catchments which are homogeneous to my catchment where I want to do the estimation. So that is the selection of the homogeneous region or selection of the region. That is the first step. And the second step is that once you select the region, then you have to develop some kind of estimation equation. It may be regression or other approach. Maybe you can use artificial neural network, you can use regression, you can use, there are other approaches as well. For example, you can use probabilistic rational method, which was recommended in 1987 ARR. So these are the different approaches. So that is the estimation equation. So that is the selection of the estimation equation. So what are the data needed to develop RFFE technique? So if you want to develop your own RFFE technique, what are the data needed? Sanjim, can you explain what are the data needed?
Sure, first it's the flood data at the gauge sites. So the stream flow data, the annual maximum series data, and also the catchment characteristics that are relevant to production of floods. For example, the characteristics that can affect the rainfall runoff relationship and stuff like that.
So what are the characteristics you are using in your thesis, because you are doing a thesis in this area?
Sir, lack of make sure that there's not much urbanization in the site.
No, that's the selection criteria of catchment. I'm asking that what are the catchment characteristics you are using as predictor variable in your.
Oh, okay. Oh, sorry. Okay. Yeah. I'm sorry. So I'm using the mean annual rainfall, the shape factor, then the design rainfall intensity for 6-hour duration for 50% AP flood. These are the three used. And
There is one
also
more
the area, catchment area. Yes, yes, sir.
So these are some of the important characteristics that you can use in developing your RFFE model. Accuracy consideration, how accurate they are. They have a lot of error and uncertainty in the technique. That's why more research is needed in this area so that we can reduce the error and uncertainty for both at site and regional flood frequency analysis. So in this approach, in this ARR, we applied region of influence approach for forming our region. So who can explain what is region of influence approach, ROI approach? Who can explain what is ROI approach?
So the basic knowledge on the region of influence approach means to form the regions, have the flexibility to around the target sites of interest to estimate. Like if we would like to estimate number 1 stations, then we have select any one of the station on that near about that, and we can choose another regions surrounding of that regions to make or form regions. And
that means that for every station there will be a different region. Is that right?
Yeah.
For every location you have a different region because you are changing location. If you are changing a location of your ungas catchment, your region will change.
Yeah. So that means the one station might be in different groups. Is it right, sir? So in that case, any particular station might be a member of different station or more than one region.
Yeah, that is true as well.
Yeah.
So one station, gauging station will be contributing to many regions, nearby regions, because that can be a member of other groups as well. And in simply for every location, you will form your own region, which is very complex in doing it, because if you want to do that apply in practice, then it will be very difficult. That's why in ARR 1987, they said, no, we don't, because at that time it was not like the computer power was not that much. So they said, okay, we can consider New South Wales as a single state, as a single region. Victoria can be considered as another region, something like that. Queensland can be considered another region like that. So that is called the fixed region approach. But region of influence approach is much more advanced than that. So it means that depending on your location, you can select your own region. So RFFE software, we have the optimization within the software. So it can select the region for each location based on some optimization criteria. So ARR RFFE technique applied parameter regression technique. So in parameter regression technique, they applied the LP3 distribution. So LP3 distribution, you can use log or ln, it doesn't matter. So we applied ln qx equals m plus kxs, where m is the mean of the log data. In this case, log e. And s is the standard deviation of the log data. You applied LP3 distribution in your quiz, last quiz, I guess. And what is kx here? What is kx or kt?
It's the frequency factor for LP3.
It's the frequency factor. So only I'm hearing the answer from only 2 students, Ali Ahmad and Tanjim, which is really good. But what about other students? I can see 39 students participants. So other students, they are not responding to anything. So what's the reason behind it? Probably you're understanding everything or you're not understanding anything. Okay, so this is the like the parameter regression technique, because in that model, our FFP model, we regionalize the parameters of LP3 distributions, which are the location, scale, and shape, which is the mean, standard deviation, skew. So we developed equation for mean, standard deviation, and skew as a function of catchment characteristics by using regression analysis. And we use the GLS regression, Bayesian generalized least square regression. So this could be a question in your exam, in your quiz, that in RFFE model, what type of regression approach was applied to estimate the regression coefficients. So the answer is based on generalized least square regression. Then we may ask further, what is the advantage of generalized least square regression over the ordinary least square regression? So you can recall that I showed you to do regression analysis in SPSS, is that right? Can you recall that I demonstrated how to do regression analysis in the SPSS? Motasem, can you recall? So did I show SPSS in a class?
Yes, you did.
So we applied OLS regression for that, ordinary least square regression. So what is the difference between OLS and GLS regression? Who can tell me this?
Just my basic understanding says that in ordinary least square, we just see the relationship between two variables, dependent or explanatory, and ordinary and generalized least square, it is mainly used for when there is, consideration of interset independency or interset dependency, something like that, or within the dependent variables and the independent variables.
I think he is right. So what is happening is that, we are forming our reason. Say, I want to estimate flood quantities at Kingswood and at a particular location where I don't have any data, then I am selecting, say, around 30 stations nearby around that location. And I have the annual maximum flood series data for each of the station. But there is correlation between the data of one station with another station. Because most of the time when the flooding happens, it happens due to the very long duration rainfall event. Those kind of events generally covers a big area. So it means that if I have flooding in one catchment, there will be flooding in the nearby catchment at the same time, generally. So that means there is a high correlation between annual maximum flood data of one station with another station. This is called spatial correlation. This is different to serial correlation. The serial correlation is for a particular at a given site, the correlation between one year with the previous year. That is called serial correlation. It can be lag 1, lag 2, lag 3, and so on. So interstation correlation means that data of one station is related with another station. So I showed you how to find the correlation coefficient in the lecture or in the tutorial class. So the GLS regression considers this correlation matrix to reduce the amount of information, because if they are correlated, it means that they are having the same information. That means that they are coming from the same rainfall events or something is sharing. So it means that our net information is less than the information that we are getting from the data sets. So this is GLS regression was developed by Jerry Stedinger in Cornell University. And they developed in 1985, 1986. So it is a very sophisticated technique. And we applied that in our RFPP model, and Khaled Haddad, he developed this program in MATLAB to do the analysis of GLS regression. So this could be a question in your exam. What is the difference between ordinary least square and generalized least square regression? So these are the theory that, what are the theory we applied to develop the RFP technique. And then this is the database that we used, that the 798 catchments from humid coastal areas and 55 catchments from arid and semi-arid areas of Australia. So this is the distribution of the data from different states that we used in our development. Different states, how many stations we used, what is the estimated data length, 20 to 82 years, 34 is the median, and this is the area of the catchments that we used in our data. You can see that for Northern Territory, we use some big catchments, few big catchments as well, because there are not enough data stations. So the our committee decided that we can relax the upper bound of the catchment area for Northern Territory. So what are the catchment characteristics that I used in this approach? Catchment area, design rainfall intensity at catchment centroid in millimeter per hour for 6-hour duration and 50% AEP. So how we can obtain the catchment area for a particular location? How can we estimate catchment area? Anybody done this catchment area in any other subject?
So is it by aerial imaging of the catchment?
No. That can be used, but really there are simpler techniques of doing it.
Can't you use that grid method where you fill the area with squares?
That is true, but you have to use a map. Is that right? What kind of map you use?
Not sure, sir.
There's a map called topographic map. Have you heard the name of topographic map or topo map?
Yeah.
So you use topographic map to locate your catchment and draw your catchment boundary, and then measure the area. You can use planimeter or you can count the square, because in this type of generally 1 to 100,000, 1 is to 100,000 generally in Australia. So that means that 1 centimeter becomes 1 kilometer. So that means 1 grid is 1 square kilometer. Then you can count how many grid within your catchment. That is a crude way of doing it, but you can use planimeter and other methods to measure your catchment area. And then how you measure your design rainfall intensity at catchment centroid? How you can do that? Where you get this information?
So it's in the IFD website, the Bureau of Meteorology website.
That's right. We did that. I think last tutorial class we showed that. Is that right? So design rainfall intensity is Bureau of Meteorology website. At any location, you can get your design rainfall intensity, but in RFP software, you don't have to do it because it automatically links with the B1 software and it automatically gets the reading for you. And then the ratio of the design rainfall intensities of these two intensities, 2% 6 hour, 50% 6 hour. This is again done by the website itself. And then shape factor. Shape factor is defined as the shortest distance between catchment outlet and centroid divided by the square root of the catchment area. So if the shape factor is high, what does it mean? So I have two catchment. One catchment shape factor is 3, another catchment shape factor is 0.5.
So the bigger,
so what does it mean?
So the bigger the shape factor, it means the shape factor might be in the hilly areas or something very up and down areas.
No. You look at the definition.
This is the distance between the catchment outlet and the centroid, and divided by the square root of the area. So that, I mean, the slope may be high?
No. Sanjim?
Maybe the, sir, if the distance between the catchment outlet and the center is really long, really high, but the area is really small, then the shape factor will be really high, which means that the catchment is like shaped like very narrow, like a
And
really long, yes, sir, elongated, yep, but not really
very long and elongated. That means when the shape factor is higher, that means that catchment is quite long and elongated. And if the shape factor is small, then catchment is kind of round catchment. So that is the measurement of the shape factor. Then of course, RFP technique divided Australia into number of regions. So this is the South East Coast division, which is the biggest region you see here. So this is one region in our RFFE model. Then this is the arid region, which is the central middle Australia. Then this is the boundary, fringe region in between. And then Tasmania is another region, and near Adelaide is another region. Southwest, Western Australia, another region. And the Northern Territory top end is another region. But when you're applying the software, you don't worry with the region because depending on your location, software itself will identify where you are and which region you belong to. And then it will automatically select the region for you, and it will automatically do the equations, everything for you. So it's a very user-friendly software, but it has a lot of complex mathematics in between and complex technique. And probably in the whole world, RFFE technique in Australia is the most advanced. And some of other countries, they are trying to follow it now. Canada, they have already adopted this kind of approach. And some other countries, they are trying to do it as well. And there are some like the sum of the accuracy of this technique. So this is the kind of accuracy. So you can see the error level for different return period. So 1% for 1% flood, which is Q100. For the biggest region, which is the East Coast region, median error is around 59%, which is quite high. It's quite high, so we did better model to reduce this error, but at this moment we don't have any better model, so that's why more research are needed to increase the accuracy of this technique. So people can do more PhD on this approach. At least 3 or 4 PhD students worked on this approach when we are developing it. It took from 2005 to around 2015, around 10 years of research in developing this software and this approach. Impact of climate change is an important factor which has not been considered in this RFFE model. So somebody has to do more research to incorporate the impact of climate change on this RFFE model. So this is the model that I think I showed you that in your tutorial class. So this is easy to apply, but it's not easy to understand the results and the meaning, what it's doing and where could be the error and this kind of things. So any question on this? Okay. So it's all understood by everybody, which is good. Okay, so now we'll give.
Sir, can we just make one one issue?
Okay.
Like for the model validation, RFFE model validation, we do leave on out validation.
That's right.
So, yeah. So on that case, we just take one site from the analysis for leave on out validation. So is there any basis? So which one site would be left out, or it is randomly one by one?
You have to do one by one, starting from one by one, and you have to do at least one time for one catchment. So it is done randomly, so that one catchment is randomly out. Very easy to do it in computer programming.
So it depends on researcher judgment. Just one, and then we take another one like this.
You can start the first one. You can start with the first one. So leave the first one of the catchment. You can make a list of the catchment by some criteria, and then you remove the first one and you develop your catchment by n-1. And then apply your model to the catchment you left out, which is the catchment number 1. And then you bring back that catchment again, and then you take number 2 out.
Yeah.
And you go up to the end. So this is called leave one out validation.
Yes, yes.
There are other validation techniques like the split sample validation. So for example, Tanzania is doing that. For example, you can leave 30% of the catchment out. So if you have 100 catchment, then select randomly 30 catchments from that and leave that out for testing. And you develop your model, if it's regression model, whatever model it is, then you apply your developed model to the catchment, 30% catchment you left out. And you estimate your error of the model.
Okay. Okay.
That is called split sample validation technique. There is another validation technique, is called Monte Carlo validation technique, which is that you sometimes you select 20% out, sometimes you select 10% out, sometimes you say, okay, 50% out, 40% out, and you repeat that 10,000 times. And every time you do the estimation error, and that gives you more accurate estimation of the error of your model. Khaled Haddad did that, and he published a paper. We published a paper in Journal of Hydrology and Monte Carlo cross validation as well. But we found that it's very similar to one at a time validation. So finally, we thought that one at a time validation is good enough for this approach.
Okay.
Okay, so I'll leave it here and then 5 minutes break, and then I'll go to the next lecture.
Sir,
Yes.
sir, do we have tutorials today?
Sorry?
Do we have tutorials today?
Of course, there is tutorial class in the afternoon. Yes, we'll show you how to apply the man-candle test and Spearman row test using R to examine the trend in the data, which I'll be discussing in the coming lecture in next 1 hour. And we'll apply our program to test that method. So you'll be learning R into this tutorial class. Very important. Okay, so I'm giving you a break now. 5 minutes break, and then we'll come back to the lecture. Okay, we can start our lecture 8. So in lecture 8, I'll be discussing trend analysis of hydrological data. So what do we mean by trend? By trend, we mean a particular pattern in the data. So in particular, by trend analysis, we mean that whether the data is showing any sign of change, either increasing or decreasing or some other way with respect to time. For example, somebody may say that rainfall is decreasing in Southeast Australia. So that means that somebody is doing the analysis of the rainfall time series data and finding that there is a trend in the general trend, or we call it monotonic trend, that is increasing or decreasing. And hydrological data is many different types of data. Hydrological data, for example, the temperature data, relative humidity data, rainfall data, stream flow data. These are all regarded hydrological data, water quality data, for example. So at the beginning, I will discuss what is trend analysis. I'll try to define it a little bit more. Then I will introduce two most important tests that we apply in trend analysis, which is Mann-Kendall test, MK test, and Spearman-Rowe test, SR test. So what is trend analysis? Long run increase or decrease over time. So that means that we have to have a long period of data. And that data, if it shows an overall upward or downward movement or trend, then we say there is a trend in this data. Of course, we have to do a hypothesis testing whether this trend is due to the sampling variability or it's the real trend, because we don't have the population. So its data generally should be over a long period of time. For example, in case of Australian rainfall or stream flow, if somebody is doing the trend analysis with 10 years of data, that will not be very useful, because the La Nina and El Nino events in Australia, they can remain 3 to 7 years. So that means that our data series should contain multiple episodes of El Nino, for example. Otherwise, the trend will be misleading, because during El Nino period, rainfall in Australia, Southeast Australia, say New South Wales, generally smaller than the La Nina period. La Nina is the wet period. So this El Nino, La Nina is really determined by the sea surface temperature. It's basically the difference in pressure between Northern Australia and South America. So trend analysis is widely used in hydrological data analysis. For example, when you are doing flood frequency analysis, you should first check whether there is a trend in your data. If there is a strong trend in your data, then you cannot apply the traditional flood frequency analysis that we have discussed so far. So you have to use non-stationary flood frequency analysis, which is quite complex. And we are not discussing that in this lecture, because this is a kind of introductory lecture in this subject. This is a matter of postgraduate or PhD level, like master's and PhD level things, to do the non-stationary flood frequency analysis. One of my PhD students, Elias Isaac, he conducted a research on this. Currently, I have another PhD student, Ataur Rahman, who is doing this non-stationary flat frequency analysis for Australia. So there are two types of approaches one can use for trend analysis. One is the non-parametric approach. So non-parametric approach, where you don't assume that data has a particular distribution. This non-parametric approach is particularly useful for the data set which are not distributed according to a normal distribution. So non-normal data. And also for the censored data like your peaks over threshold series, for example, which is a censored data. So what is time series data? If you want to do a trend analysis, you must have a time series data. So time series data is that with your magnitude of the data, you have a time attached to it. For example, annual maximum flood data is a time series data. Annual maximum rainfall data is a time series data. Daily rainfall data is a time series data. Even the hourly rainfall can be time series data as well. In fact, Australian Bureau of Meteorology, when they record the rainfall data, they record it at 3-minute interval. So every 3 minutes, they record the rainfall at some of the pluviograph stations. So you can use that kind of data in your research as well. I have used that kind of pluviograph data for 6-minute interval for many stations in Australia in my research and the research of many of my PhD students as well. So in this time series data or trend analysis, sequence of the observation is very, very important. So that means that you have to order your data chronologically with time. Starting with earliest year, say I data 1900, 1901, 1902, and something like that to the present time. So time series data is a two-dimensional plot of the time series plot, and vertical axis measures the variable of interest. It can be rainfall. So really, this is your say rainfall, and this is your time. So your rainfall can be like this. So sometimes there is rainfall, and most of the time there will be 0. So so that is the time series data. Horizontal axis is time. So this is an example of time series data. So this is the month here, monthly southern annular mode. So this is the month, and this is your sea surface temperature anomalies. So that really tells that your El Nino and La Nina period. So one of our PhD students, Melanie Lobridge, she conducted trend analysis for infiltration losses for eastern New South Wales. So losses is the amount of rainfall when in the rainfall runoff process, when there is rainfall on a catchment, if the catchment is dry, then part of the rainfall will be entering inside the soil, and that will not appear to the stream or river immediately. They may never appear. This is called the loss. So there are two types of losses in rainfall runoff modeling. One is the initial loss, another is the continuing loss. So did you do your surface water hydrology before? Anybody?
Yes.
Have you done your surface water hydrology?
Yeah.
So can you define what is initial loss and continuing loss?
So initial loss, I think, is when the rainfall just starts, and even before there is a rainfall buildup. So up until that point, the water is lost. What I'm trying to say is, for example, if the rainfall starts now, maybe in the next 2 hours, there won't be any water building up, because in those 2 hours,
Any water in the river.
Yes, sir.
So before, like the rainfall happening before the start of the surface runoff generation.
Yep.
So that rainfall has been infiltrated or entered into the ground. So that is called initial loss. And what is continuing loss? CL.
That's a loss. Like, for example, if there is whatever magnitude of rainfall that is happening, the same amount won't be in the runoff. So whatever's the decrease, that's the amount that's been like that's the continuing loss.
Yeah, that is true. So continuing loss is really even there will be some infiltration during the runoff. When the runoff is happening, even some water will enter inside the soil. Some water will be evaporated. Some water will be intercepted by the vegetation. So all of this forms continuing loss.
Bro, it's fucking hot. I don't know what to tell you. I'm waiting for the aircon.
So now we can see some catchments here. So you see this is a boundary of a catchment. This is another catchment here. This is another catchment. So previously we defined the shape factor. So which of these three catchments will have the highest shape factor?
The second
We defined shape factor in our previous hour of lecture, shape factor.
The second one down.
Second one down, because this is the center of the catchment. You can see this is the centroid, and this is your catchment outlet. So the distance from centroid to the outlet, shortest distance, divided by square root of the catchment area. That is your shape factor. So Melanie Lobrez, she selected this kind of catchments. It's an example here. And you can see initial loss here. So this is, you can see initial loss on the y-axis, and this is the time in x-axis. And you can see that there is a general trend that initial loss is increasing with time. But for another catchment, is decreasing. Another catchment is increasing. Another catchment is really a little bit decreased there. So different catchments is behaving in a different way. So really, there is some trend, but you have to identify the reason why this is happening. Is it due to climate change, or due to some characteristics of the soil or land has changed, or something has happened? So if you want to know more about this trend of these losses, you can read this paper published in 2013 by Melanie Lobrez and myself, if you want to know more about it. There are some limitations with the trend analysis, because most of the time we do the trend analysis to see the impact of climate change on the rainfall or runoff or any other variable of interest. So sometimes this trend may be due to other factors than climate change. For example, there might be change in instrumentation over time. There might be some site-specific effects. In that case, we have to understand the data, and we have to understand why this spurious trend is happening. Or like when you see a trend, we have to doubt ourselves, and we have to do further investigation to see why this trend is there. We have to find some physical explanation. And if we don't find any physical explanation, then we can say, okay, this change is happening due to climate change. This trend is happening due to climate change. So multiple comparison problem. So that means that if I see rainfall is changing at Penrith, for example, rainfall say at Penrith is increasing with time, and then at Parramatta is decreasing with time, and then say at Windsor is decreasing with time. Say another site, say Sydney CBD increasing. So all different sites, some is increasing, some is decreasing. So that kind of thing indicates that it may not be due to climate change, because if it is due to climate change, then there should be a reasonable pattern. So most of the stations should be increasing, or most of the stations should be decreasing, because climate change like El Nino, La Nino, or the effect of climate change does not only affect in particular city, Penrith or Sydney, it should affect the whole New South Wales or most of the New South Wales or something. So it means that there should be a test field significance. For example, if I have 100 sites in New South Wales, I have selected 100 rainfall stations in New South Wales, then I should find say 70% station showing downward trend. Then I can say, okay, 70% of the stations showing downward trend. So we may conclude that the rainfall in New South Wales is changing downward. If the record length is too short, then when you are drawing some conclusion, you should be very, very careful about the conclusion that you are drawing of from the trend analysis of the short data, because the short data may be a completely sampling problem. It is nothing with the population. So you should be very, very careful. Particularly in case of Australia, I mentioned to you that if your data length is less than 30 years or so, your trend result is really not very meaningful. So there are two types of approaches for trend analysis: parametric and non-parametric. So parametric means that we assume that the data has a particular distribution, often Gaussian or normal distribution. For example, I have say 150 years of temperature data at a particular location, and is following a normal distribution. If I can do a histogram, it looks like a normal distribution. I can do some testing as well. And then we can use the parametric approach, such as simple linear regression. Non-parametric approach is that it may not be a normal distribution data, and there could be gaps in the data. There may be outliers in the data. Some values are very high, some values are very low. Then in that case, non-parametric approach is more preferable. It's preferable. Okay, so what do we mean by monotonic trend is it's really continuing trend. So like monotonic trend is something like a spontaneous graph. Something is like this. This is not a monotonic trend in that sense. Of course, if I draw a line in between, then I can find a monotonic trend. So parametric example is the like linear regression. If you do a linear regression analysis, and if your regression slope is like y equals minus bx plus c, and this minus indicates a downward trend. If this b is plus, it indicates a positive upward trend. Non-parametric tests are Mann-Kendall test, Spearman's row test. These are the two most commonly adopted approach in hydrology. They are more robust to violation of assumptions. As I mentioned before, that your data may take any distributional form. You don't have to be normal distribution. So in doing the trend analysis, if we see a trend in the data, say we have a trend in the data, so you have to do a hypothesis testing whether this trend is significant, statistically significant or not. We have to do a hypothesis testing. So H0, what is H0? What do we call H0 and H1? Is H0 is the null hypothesis or alternative hypothesis? H0, is it null hypothesis or alternative hypothesis? Who can tell me?
Sir, H0 is null hypothesis, sir.
H0 is null hypothesis and H1 is the alternative hypothesis. So H0 telling the distribution of xi, xt is same for all t. So it means that there is no trend in the data. And alternative hypothesis is that opposite to that. So there is a trend in the data. Sometimes we want to find out the quantity of trend, the rate of change happen in the slope of that line as well. So Mann-Kendall test is most widely used test. So today I'll be using our software to show how to do the Mann-Kendall test. This is the most frequently applied test in our hydrology or in many disciplines. This is a rank-based distribution-free test, or it means that you have to rank, you rank the data and you don't bother with the distribution of the data. So this test, the null hypothesis in the MK test tells that the data x1, x2, xn, which is the annual maximum flood data of years 1970, 1971 up to say 2020, they are sample of n independent and identically distributed random variables. So it means that at that particular location, I may have thousands of years of annual maximum flood data, but I have taken 40 years of data. That is a random sample of that population. Then the MK test statistic is given by a statistics S, which really tells you like the between xi, xj and xi. So it means that say I have first value is 5 and next one is 7. Then next one is 2. So xj minus xi, what is the sign of that? Is it negative or positive? 7 minus 5, is it negative or positive?
Positive.
Positive. So I am getting a positive for the first case. Then 7 minus 2 minus 7, what is that? 2 minus 7, it is a negative, is that right?
Yeah.
So for each of the data points, you find out, you subtract so difference between these two, then these two, then if I have 4 here, then these two and so on, then you will get some positives and negatives, is that right? So the value of S will be plus 1 if greater than 0. The difference between this is greater than 0, which is positive. And it is 0 if they are equal. It is minus 1 if otherwise, the way I showed it here. Then the Mann-Kendall, Mann 1945 in a paper, and Kendall 1975 in another paper. They combined these two techniques basically. Kendall worked on the Mann. That's why they call it Mann-Kendall test. So it tells that if n is greater than 8 or equal to 8, then we can find the expected value of this S is 0. So it means that if there is no trend, then basically your sum will be 0 because there will be some positive and some negative, plus 1 and minus 1. And if you take the average of that, it will be 0 if there is no trend in the data. Is that right? Do you agree with that?
Yes, yes, sir.
Because there are some positive and some negative, and if there is no trend, then the equal number of positive and equal number of negative. And if there are more positive, then it's positive trend. If there are more negative, it's a negative trend. But how more? Because if it's only one more, then the question is coming, like I have say 7 positive and 6 negative. Then if somebody says it's a positive trend, then somebody may say okay, it's only one difference and you would have taken a different sample of that population, it could have been different answer. Then the problem is coming at the sampling variability problem, hypothesis testing is coming. And the variance of S is estimated by this equation n times n minus 1, 2n plus 5 minus I equals 1 to L and TL, TI, L minus 1, 2I plus 5. So L is the number of ties. How many groups we made there? So under the null hypothesis, the standardized test statistics, Z, and its corresponding p-value are approximately normally distributed. So standard test statistic ZS is estimated by S minus 1 divided by sigma for S greater than 0 and S less than 0 and S equals 0. The null hypothesis, which is there is no trend, is rejected at a significance level alpha if Z, this ZS coming from the data is greater than minus Z critical. So that means that in our standardized normal distribution, if I have this is the standard normal distribution, then really this ZS is falling in this region here, because this is the minus area of the normal standard normal distribution. So your ZS is coming in this area here. Then you reject your null hypothesis and say the hypothesis that there are no trend in the data is rejected. So that means that there is a trend in the data. My PhD student, Elias Isaac, he did a lot of trend analysis in Australian catchments, for many catchments in Australia. And we published that in Journal of Hydrology. So if you want to know more about this trend analysis, you have to do additional reading. And I recommend that you can read this paper to understand it more about the implication of trend analysis. And so in his paper, what he found is that the annual maximum flood data in Australia, in Southeast Australia, in New South Wales and Victoria, most of the stations are showing a downward trend. So that means that indicates that rainfall is decreasing in this region. And we found that annual maximum flood data in Northern Territory is giving positive trend. So it means that generally the rainfall is increasing in the Northern Territory region. So that are the general findings of this research. But currently, Ataur Rahman is doing PhD again on this topic. And he will be using additional data because Elias used data up to 2004. So now we have 16 years more data and there are new advanced technique. So Ataur will be applying this advanced statistical technique to examine the trends in Australian annual maximum flood data. And he is working in collaboration with Professor Taha Ouda from Quebec University in Canada as well. So now there's another test. This is also a non-parametric test, Spearman row test, SR test. So this really assesses how well the relationship between two variables So that means really if there is a serial correlation between the data points, say I have a data 5 and 7 and then 9 and then 11, something like this, then there is a strong correlation. That means that 5 and 7. So it means that I can immediately tell that next one will be higher than 7. And the next one is higher than 9. So that means that it has a strong positive serial correlation. But generally the flood data rainfall data is not like that, it's random. It may be 5 and then next one may be 2, and next one may be 9, the next one may be 11, next one may be 3, annual maximum flood data rainfall, that may happen like that. So basically, it really relates this correlation, serial correlation, and test that whether it is significant or not. So if there is no correlation, there is no serial correlation, then correlation 0. If it is negative correlation, it's -1, perfect negative correlation, perfect positive correlation. So perfect negative correlation is something like this, that all your data point is falling on the line. And perfect positive correlation is something like this, that all your data points, observed data point is falling on that line, regression line, basically. So this method tells that if I have a data set xi, say if I have 50 years of data, then I have 50 values there, 1 to n. The null hypothesis H0 of the SR test against trend test is that all xi's are independent and identically distributed. And alternative hypothesis is that xi increases or decreases with I. That is, the trend exists. So in first case, it's completely random. So that means there is no trend. And in second case, there is some kind of trend, that there is a kind of general increase is happening or general decrease is happening. So that is really given by this test. This test statistics is given by D, but D equals 1 minus I equals 1 to n, and there is 6 there, and Rxi minus I square of that divided by n times n square minus 1, where Rxi is the rank of the ith observation and xi in the sample of size n. So it is the rank of the data. Under the null hypothesis, distribution of D is asymptotically normal, with the mean and variance as follow. Expected value of D is 0, and variance of D is 1 divided by n minus 1. And the standardized test statistics is obtained by ZSR equals D divided by square root of VD, the variance of the D. The p-value of the MK test can be estimated by this equation here. P equals 0.5, which is the middle point of the standard normal distribution, minus phi function of absolute value of z, where z is estimated by this equation here. If the p-value is small enough, the trend is quite unlikely to be caused by random sampling. So it means that if our p-value is very small, then the trend is genuine. If you want to know more about this test, then you can read this paper by Yu et al. 2002. Power of the Mann-Candela and Spearman's row test for detecting monetary trends in hydrological series, Journal of Hydrology, published in 2002. So in summary, we have discussed hydrological trend analysis, and we introduced two non-parametric approaches, MK test and SR test. Mann-Candela test and Spearman row test. So these tests are widely applied. Non-parametric tests are preferable to parametric tests for hydrological data, because most of the time, hydrological data like the rainfall or runoff they do not follow a normal distribution. And most of the time they have gaps in the data, and they may have outliers in the data. So in our tutorial class today, we'll be discussing the how we can apply these two tests with our annual maximum flood data for two sites in the 2 days tutorial class. So do you have any question on this lecture? Anybody has got any question?
So as a final ask regarding the project design, the report.
So you want that we should discuss the project report. Okay, so what is your question with the project report?
Well, in the point 4,
Can you
comparing
read the
the 4
point 4?
data. Just give me a second. Let me just open the file. Sorry. Project. Yes. Yes, point 4 says, point 5, it says compare results of steps 1 to 4. So how we will be comparing them? Doing the linear regression, or how we can compare them?
So comparison of different approaches. So you can do comparison by finding the percentage difference between different approaches. You can plot the different quantile estimates on the observed data. By plotting the observed data, you can superimpose your different distribution, different methods, and then you can see which method is coming closer to the observed data. I showed that in some of the tutorial class, how we can plot that kind of data. So, and you can also apply some goodness of fit tests to tell which of this method is the best for a particular sample. Another way is that if you are applying 5 different approaches and say 3 or 4 of them, they are giving very similar answer, and one is giving very dissimilar answer, then you may assume that majority of the approaches are giving some answer which are nearby. So that may indicate the accuracy of the estimation. So in hydrology, that is widely used, that if different approaches giving similar answer, then that gives a more confidence that our answer is probably correct. So in hydrology, there is no correct or wrong answer in that sense, but there is some optimum answer given the data set and given the computer power or given the expertise you have available. So, so it's really a kind of subject or discipline that is very empirical. It really applies a lot of statistics, a lot of probability concept, a lot of variability, uncertainty in the estimation. So that's why this subject is not like some other subject, for example, structural analysis. You are dealing with the material properties. So say if you consider reinforced concrete, you are using cement, gravel, and water to make your concrete, and then you are using your reinforcing bar. So if you consider a particular mixed design, and if you want to get 20 MPa concrete, then probably you will find that most of the time, if you take the test sample, you'll find that some of them 17 MPa, 18 MPa, 21 MPa, 22 MPa. So it may not vary quite a lot generally. But in case of hydrology, you have seen that from the flight example that I showed, that your expected value is around 15,000 meter cube per second, and your upper confidence limit is around 100,000. So you are dealing with a lot of uncertainty. It's a kind of very random walk, or you are moving in a territory of unknowns and uncertainty, basically, in hydrology. So
yes, thank you.
So that is the way of comparison. So really, there are many ways you can compare it.
And will you be checking our names for this session or not?
Sorry?
Will you be checking the names? Will you be marking our names?
Yes, you will be marking the names. Before that, I would like to say, do you have any question on your test? Test is next week, is that right?
Yep. It's next week.
Do you have any question for the test?
So will you be making an announcement based on what contents will be in the test, or is it just safe to assume weeks 4, 5, and 6, like it says in the learning
No,
guide?
no, it's on the learning guide.
Yep, cool.
It's in the learning guide. What are the lecture, how it will be tested? So we can look at the learning guides. Let us see.
Cool. And one more thing as well. In the beginning of the lecture, you said something about the what was the first program we used called? The one you were showing us how to use?
Is it Flyke?
Yep, that's the one. Did you say that was going to be tested in it as well?
No, because you don't have the availability of the Flyke. So I'll be giving R, because R should be available to everyone, R and Excel, not the Flyke.
So another R one will be there.
R will be there, Excel will be there. So you have to use R and Excel.
Cool.
And the ARR book, that is book 3 is very relevant. So book 3, some question will be coming from book 3. And the chapter 2 and chapter 3 both.
So because there's Excel, will you be providing the input numbers beforehand?
I'll provide the data set before.
Okay.
Before the test, so that you can copy the data from the views.
Yeah,
so
sounds
you
good.
don't have to type it up. Yeah.
Thank you.
Any other question? If not, then Saika, can you take the Saika? Is Saika here? Should not be here probably. Probably I have to take the role, I think. Yeah. I think I don't have the role sheet with me at this moment. Is Saika here, Saika?
So we can just type our name in the chat, and when
Don't
recording
worry, that's fine, because there is no mark in the role, so that's fine. Don't worry.
Okay.
Okay, I think that's all for today. So see you next week in the test, and it will be very similar to the repeat quiz last time. It means that it will be 1.5 hour time you'll get, and so it'll be very similar to the last quiz, repeat quiz. Okay, I think that's all for today. Unless you have any more questions for me.
So submission time we will get the as we did earlier.
For master's thesis, yeah, you should email the question to me after the exam, so 1.5 hour. So for master's and PhD students, you should also email me the solution within that time.
So earlier we sent it by 3 in
because we gave you too much time last time, so this time we are giving you less time.
Okay.
Okay, I think that's all for today. So see you in the afternoon. Afternoon we have the tutorial class, and we'll show you how to apply the R for doing this trend test, which is very interesting and very important experience for you, because this is widely used in practice, and many people they cannot apply it because in Excel it's very difficult to apply, but in R it's very simple. Okay, thank you. That's all for today. Bye.
Assalamu alaikum.
No, sir. So let me stop the recording.